So let's look at another example with our sampling distribution of proportions. So just to kind of outline what these questions will look like, you'll be given some population proportions. Something we'll need to do is check the central limit theorem, which when we do this, it'll entail just check off independence, check randomization, and then the piece where you'll need to show work as your proof that we have a normal curve is the success-failure condition. And with that, you'll need to show that n times p is more than or equal to 10, and n times q is more than or equal to 10. Then from there, you can set up your parameters. So the mean of the distribution, which will just be equal to your population proportion. Standard deviation will be a big square root of p times q over n. Then from there, we have our bell-shaped curve, and we can start making calculations. So, information on a packet of seeds claims that the germination rate is 92%. So this right here is something printed on the packet, so that would be a population value. It's what we expect when we plant those seeds. We expect 92% of them to work. So that's our population proportion, is the 0.92, which means Q is 0.08, coming from a 1 minus 0.92. Then what we're going to take is a sample size of 160. So we're going to look at this sample of a single packet of 160 seeds. So first step is that we're going to discuss the conditions, which is our central limit theorem. So, independence. Independence and randomization, again, you can just mark those off. I just want to basically see that you thought about them. That's all I'm requiring for our course. But just in case you're curious as to why, independence, because how the seeds sprout would be independent of each other. You could also use that 10% condition that we're looking at 160 seeds out of all seeds. So 160 seeds would be less than 10% of our population. Randomization should be the idea that when they put this packet together, they're randomly selecting 160 seeds. That should be part of the process. So we'll assume that's nice and random. But then the part that we really need to show work is the success-failure. And with that, we're going to take our sample size of 160 times 0.92 and 160 times 0.08, and making sure those are larger than or equal to 10. This will be 147, and this will be 13, which are both more than or equal to 10, so we pass that success-failure condition. So because we pass all three conditions, we know that we have a bell-shaped curve. It basically allows me to draw this for our distribution. Nice bell-shaped curve. Alright, so defining the distribution, and actually I need to save that picture for part C. Defining the distribution and its parameters. So the parameters are population mean of our sample proportions. You just copy the population proportion, so 0.92. Standard deviation, we need to calculate, taking the square root of 0.92 times 0.08 divided by 160. If we plug that into a calculator, we should get a 0.0214. So to define our model, it's normally distributed, centered at 0.92, with a standard deviation of 0.0214. So, to get a sketch of the model, we have a bell-shaped curve. The center of that curve will be a 0.92. And we'll just go to standard deviations above and below, and we're moving by units of 0.0214. So this will be a 0.9414. This will be a 0.9628. And here's a 0.8986 and 0.8772. So with this number line, again, just to emphasize, this is a number line of percentages. Or specifically, in fact, I'll write this down here, it represents the percent of 160 seeds that germinate. The idea being we expect 92% of them to germinate. Maybe we could see about up to about 96% of them germinating, down to close to 88% of them germinating. We get this idea of expected percentages from this number line here. So what's the probability that more than 95% of the seeds germinate? So what this would bring through is 95% of the seeds. So this is giving us a number along the number line. Or really you could think of this, it's a probability question, which means we want to find area under the curve. I know in the previous section with normal distribution, we get kind of used to if they give us a percentage, they're telling us area under the curve, but that switches here. With proportions, they're giving us percentages. So we need to be clear of, are they giving us area under the curve, or are they telling us about a number on the number line, which represents a percentage? So because it's 95% of the seeds, it's giving us a number on this number line here. So 95% would land about here. And we want to find more than that value. So in terms of finding probability, we want to find the area under the curve that's to the right of 0.95. So get this probability of x being more than 0.95. So with that, we can go to GeoGebra. We have our mean of 0.92, standard deviation of 0.0214, and an area to the right, 0.95. Which will be a 0.0805. So for this, there is an 8.05% chance that more than 95% of the seeds will germinate. Let's even go 95% of the 160 seeds will germinate. Okay, so again, just to emphasize, this value is a probability, so it's a percent chance that we're solving for. That's what GeoGebra tells us on the right-hand side of the equation. That's telling us probability. So when we're interested in probability, make sure that's where you're grabbing the percentage. And it's just with these proportions, they're landing on the number line, so those are our cutoff values. Is that the cutoff values are a percent of 160 in this case, or a percent of our sample. Would it be unusual for only 140 or fewer of the 160 seeds to germinate? Now I threw this one in here because it's a little different, but it does give us the information for we're talking about a certain number out of our sample size. So imagine I went back to part D there, and I rephrased this question. What if I had said, what is the probability that more than 152 of the seeds will germinate? That question that I just wrote out is exactly the same as that initial question. It's just different form of units. In the question that I just wrote in blue there, it's asking in terms of a count, the number of seeds, the number of the seeds out of 160 that will germinate. And if I wrote it that way, it doesn't work with my bell-shaped curve up above, because plotting 152 on this number line doesn't work. But what I can do is go the step of thinking of that as a proportion, so 152 of the 160, well, 152 out of 160 is a 0.95. Then I have a number that works for the scale of my number line for my bell-shaped curve. Then I can plot 95%. So with proportions, and this is going to be something that comes up in the next section of confidence intervals and the section following with hypothesis tests, we're going to be applying those to proportions, which with that, we're going to keep seeing these formulas come up. We're going to keep seeing this form of the central limit theorem in the following weeks. And this will be an important idea, the mean and standard deviation. So formulas we're going to be using pretty much over 3 weeks here. And something that comes up is that with proportions, they can form questions in kind of 2 different ways. They can describe it as a count out of your total sample size or a percentage of the total sample size. And it's just, if they give it to you in the form of the count, you'll have this one little extra step of calculating your sample proportion first. So that's what we need to do for part E, because 140, to look at 140 or fewer on this number line, doesn't work. 140 can't be plotted there. Or it's that with these large numbers, you're just always going to get 0 or 100% out because they're so extreme in this scale. Well, what I can do is start off by making a sample proportion of 140 out of 160. And that should be a 0.875. So what we could do is, in terms of is it unusual, I mean, you could actually pretty much answer this question already. If you remember what's considered unusual for a graph is anything outside of 2 standard deviations away from the mean. When we talked about the empirical rule, so there's a 95, or rather about 95% chance landing between those values, so anything outside of there is considered unusual, and 0.875 is all the way out here. So we could answer it already if we wanted to. Would it be unusual? Yes, because it is more than 2 standard deviations away from the mean. You could also answer this by using a probability. Like, we could look at this probability of getting 0.875 or fewer. So then we could look at GeoGebra and see what kind of percentage comes out. So I need to finish that sentence. 2 standard deviations from the mean. So let's look at that probability. So less than or equal to, so I'm going left-sided with a cutoff of 0.875 to represent that 140, and that's a 0.0177. So basically there's a 1.77% chance of this occurring. So we could also ask or answer this that yes, it's a very low probability. That would work as well. Could even answer this with z-scores. A lot of different ways to show that it's unusual. We can kind of do it either visually, like we did up above here, and seeing those cut off for 2 standard deviations away. If it was inside that range, not unusual. Outside that range is unusual. Or you could use the probability as evidence as well. So that's our sampling distribution of proportions. Like I was saying, these formulas are important here because it's going to tie into what we do with confidence intervals and hypothesis tests coming up in our course. I will say right now, these types of questions about like probability of percentages are less likely to occur in the real world. Much more often we'd have a sampling distribution of means case. However, we need this as a foundation with these proportions for what we do next in the course. that's our sampling distribution of proportions.